Okay, I started it. Okay, so it's a pleasure to welcome Daniel Gromada to our seminar. He will speak about some examples of quantum graphs. Please, Daniel, go ahead.
Okay, so thank you for introducing my talk and for inviting me to this seminar. So, as you mentioned, this is the title of my talk, and the talk is based on recent arXiv preprint with the same title. Maybe before I start, I would like to mention also another article by Junichiro Matsuda, um, which has the identifier like this. I guess you can find it by his name. So this is PhD student now of Benoit Collins, who recently published also an article about quantum graphs, which partially overlaps with this article. So if you are interested in particular in the result of classification of quantum graphs, then he does this as well, and also slightly more general. So this is this result is very connected also to what I will speak about. Okay, so the outline for my talk is the following. So it somehow also is the content of the article. So first of all, I'll speak about some different approaches to how to define quantum graphs. Then I will show you how to classify how quantum graphs can be classified. So in particular, the classification over the algebra of 2 by 2 matrices. And then I will also talk about some twisting of Cayley graphs of abelian groups. Okay, so and also maybe it's good to mention that okay, I will mostly speak of course about quantum graphs themselves, and in this sense there's three different approaches are nothing new, so this is not a new result, but yeah, and also in the other 2 points, I think that the hard work has already been done somehow, but yeah, so this work somehow tries to put it together and really understand what quantum graphs are. So because this is kind of a very new topic, and I think we do not really understand it well so far. At least I personally don't feel like I understand it too much. So this is really what should be done now, and I think the first step one should do is to look at some examples. So this is the main point, what I wanted to do in my article and what I will present also today. Okay, so let's go further. I think you're familiar with the basic idea of non-commutative geometry. So just to quickly go through it, what does it mean? How does this work? Is that we start with some theory where there's usually some underlying space X, and instead of studying the space X itself, we decide to study the algebra of some functions over that space. For instance, if that space is compact, then we can take the C-star algebra of continuous functions over that space. And now the point is that commutative C-star algebras are exactly all the algebras of functions over some compact or locally compact spaces. So if you consider non-commutative C-star algebras, then those can be interpreted as some function algebras over some non-commutative spaces, although now there is no underlying space anymore. And then we can consider some structure on this space X, reformulate the structure in terms of the algebra, and then take the same axioms for the non-commutative case. So for instance, if we have some if we have multiplication on this space X, so this space X is a semigroup, then we can reformulate this in terms of co-multiplication on the algebra of functions. And hence the idea is that if we equip any C star algebra with such a co-multiplication, then this is, so to say, a quantum semigroup or a semigroup in non-commutative geometry or something. And then you can put some other axioms here, for instance, if you want to describe groups, and putting the same axioms here give you what is a quantum group. Okay, so, but instead of groups and quantum groups, I will speak today about graphs and quantum graphs. And maybe one feature I wanted to mention here is that often when going from here to here, we have some sort of ambiguity. So those axioms here, those can be formulated in several different equivalent ways. But if we transfer those axioms in the non-commutative world, then the different ways how to express them may be a non-equivalent, and therefore we have to make some choices, which sometimes might be not so obvious how to do them. So this also we will see today. Okay, so as I said, I want to speak about graphs. So first of all, what are classical graphs? So I guess you know what is a graph. So you have a bunch of vertices, and those vertices are connected with some edges. I will a priori consider directed graphs. So it might look like this, for instance. So this is a graph. So the underlying space we have here, this is the space of vertices. That's any finite set. And then the actual graph structure is given by the edges. And how to describe edges? There are two approaches here. Classically, either we consider the set of edges as a subset of this Cartesian product. So for instance, if this edge is the ordered pair of this and this vertex, right? Or we consider this so-called adjacency matrix, that is a matrix whose rows and columns are indexed by vertices, and ijth entry is 1 if there is an edge from I to j, and it is 0 otherwise. So this is basically the same thing, just I don't know, represented this with a matrix. Okay, so and now we want to quantize this, so reformulate this in terms of those algebras and maybe drop the commutativity condition. So for the first thing that's I guess pretty obvious what to do. So some finite set, this is equivalently described by an algebra of functions over that space or set. Now it doesn't at all matter what if I take continuous functions or finitely supported functions or all functions or whatever, because all those notions are the same since this space is finite, so we don't have to deal with those topological nuances. And so now what the definition, the natural definition is that finite quantum space, so finite quantum space is any finite dimensional C-star algebra. So because finite dimensional commutative C-star algebras are exactly algebras of functions over finite spaces. So if we drop the commutativity condition, we have finite quantum spaces. Okay, so and now the more interesting part is how to quantize this, either this condition or this condition. It's, well, we can choose what approach we take, and this will define a quantum graph. So I'll show both approaches. I think my favorite one is the first one, but yeah, the second one is, I guess, maybe more common. So we will get to this one also. Good. So approach one, quantizing the set of edges. So as I said, we have the finite set of vertices. Classically, this is generalized to the quantum case by taking finite dimensional C-star algebra. And now, what is the set of edges? So classically, how can we describe this? So this is a subset of this Cartesian product, x cross x. So this Cartesian product, when we want to describe this using some algebras of functions, that then we of course take the algebra of functions over the space, which is the tensor product of the corresponding algebras over X. So that's what we have here. Right, so and now we want to describe a subset here. So what we can do classically is to take the characteristic functions, right? So some function on x cross x, which is 1 if ij is an edge and 0 otherwise. And as you probably know, characteristic functions of sets, those are exactly the orthogonal projections on this C-star algebra. So a set of edges is quantized by taking an, here should be orthogonal projection in, okay, I wanted actually to write it like this. Yeah, so that's the idea. And now you might notice that I wrote here this op here. So what turns out to be more convenient is that instead of taking such a tensor product, instead of taking the second factor to be this C-star algebra, I take the opposite algebra, which is one of those ambiguities you cannot distinguish in the classical case, because in the classical case, those algebras are commutative. So you cannot say what is algebra and what is the opposite algebra. And in the quantum case, it might matter. So here it might be important. Yes.
But if it is a C-star algebra, so it's isomorphic to the opposite, isn't it?
Yeah, that's a very good point. Yes. So actually, at this point, it doesn't matter at all, as you said. This is isomorphic to the opposite algebra. Yes. So for now, it should be okay. But okay, so let's go to the second step. Now we would like to have some typical example and some examples, and the most typical examples is, I guess, the full graph and the empty graph. So classically, full graph is taking all vertices, and empty graph is taking no vertices. And of course, the corresponding projection, very naturally, for taking the full graph is you take the projection on the whole C-star algebra, right? So just the identity. And for the empty graph, you take the zero projection. Okay, so this is clear, yes. And then you have some additional notions for graphs. For instance, you can have you may want to describe undirected graphs. So this classically means that if ij is an edge, then ji is also an edge. And very natural how to generalize this to the quantum case is to say that, okay, so this A tilde, I will try to draw this as a diagram. So A tilde is some element of this tensor product. So it has somehow two outputs, and this condition says that you can that you can somehow switch those outputs. So by this T cross, I mean the swapping map like this. Okay, so this is the undirected condition, and now it already starts being important that I have this opposite here, because otherwise I would have to have, in addition, some transpositions here, or right. So now it really makes a difference, at least regarding this undirected condition. Okay.
So otherwise you'll stick in a star.
Well, yeah. So it depends what you mean by star. So typically, if you consider the tensor product of those C-star algebra, then I guess usually the star is entry-wise, so it would not change your.
Yeah, no, but I mean, you send xy to y star tensor x star. Or...
Oh, I see. Yeah. Probably this might. Yes, I guess. Yeah, I'm not sure now, but yeah, maybe. Yeah. Well, not
Why do you need a star, Willie? I don't see it.
You want to have an involution, right?
No, you're supposing to have symmetry on the tensors.
Yeah, but
why do you need
Tx,
involution?
in what sense is Tx a homomorphism?
Ah, okay.
So it's an item homomorphism, right? So it's an involution.
I don't know.
Yeah, well, one would have to figure out details, I guess. Okay, and now also.
Sorry to interrupt you so much, but when you say it's a projection, you mean it's self-adjoint. It's self-adjoint at the point.
Yeah, self-adjoint. Yes.
So the self-adjointness is with respect to the involution in each coordinate, on each factor. And this is another involution that also fixes the projection in case the graph is undirected. Okay.
Yes. Okay, and then you have this condition of no loops, classically, which, okay, so undirected means that with each edge like this, you have edge like this, and often you also want this condition that there are no loops. So loop is an edge from vertex to itself. And now, as I formulated it here, it is probably not so clear what this condition should be in the quantum world, because this definition in the classical world is somehow depends on the fact that if I wanted to formulate it in terms of those algebras, in this algebra you have some canonical basis of let's say the canonical projections delta I on the vertices, and yeah, so this condition would say something like that. Yeah, something like that. Projecting on this I is inside this projection, or something like in this sense. But here, if you take any C-star algebra, you don't have this canonical basis here. So it is totally unclear what this condition should be here. So if we want to generalize this condition, we would have to put some extra structure to the C-star algebra, which I will do in a minute. But now I guess it might not be clear what this should be. Right. So is there any other question to this?
One question. This, I mean, is any finite dimensional sister algebra is a separable algebra, so it has a distinguished idempotent. the separability idempotent, which generates the kernel of the folding map or the multiplication map. Does this particular idempotent have any special meaning in this setting?
Now I'm not sure. So again, what idempotent you mean?
So I mean, a separable algebra is an algebra A.
Mhm.
Let's call it R because A has a different meaning here. So R, so that the folding map that from R tensor R up to R that sends X tensor Y to X times Y. So this is an R module homomorphism, an R bimodule homomorphism. And the algebra is separable if this R bimodule homomorphism is a split surjection. So it has a section that is a bimodule homomorphism, an R bimodule homomorphism. When it does have a section, then this you send the section sends 1 to some idempotent, and 1 minus that idempotent generates the kernel of the multiplication map, and that's the separability idempotent. I mean, one of the two you call the separability idempotent.
Okay.
And
yeah.
you can calculate it explicitly for matrix algebras, and I suppose also for finite sums of matrix algebras.
I see.
It might mean something in terms of graphs. I don't know.
I didn't think about this, so I don't know.
Mhm.
If it, on the other hand, if it's this finite dimensional, you have finitely many irreducible representations, and for each one you have an idempotent also. So you have another idempotence. But I don't know what is going to do with the idempotence, so I will wait. Okay.
Okay.
I don't know.
Yeah. So maybe we can postpone this to the end of the talk when it's more clear what this means. Okay. So second approach would be quantizing the adjacency matrix. So again, we have the finite set of vertices. This we quantize as some finite dimensional C-star algebra. And now we have this adjacency matrix, which is a matrix with rows and columns indexed by the set of vertices. And we can quantize this. This I can also write down like this, right? It does not matter. And we can quantize this by taking here the adjacency matrix as some linear map from Cx to Cx. But here, in addition, we have another condition, namely that the entries of this matrix are zeros and ones. And again, it is not really clear what this should be in the quantum setting. So again, here we need some extra structure. Namely, how we can do this is that by noticing that this condition can be written in such a way that if I take the entries of this matrix A, then they satisfy such a condition where this obviously is not a matrix multiplication, but it's like entry-wise multiplication. So we would need to somehow generalize this entry-wise multiplication here to the quantum setting in order to generalize this particular condition. And how can we do this? Well, as I said, instead of composing those matrices, so instead of writing them like this, we need to write them, so to say, side by side, and then taking the output of the matrix, we need to somehow multiply those outputs. And in addition, so this is somehow my diagrammatical way to write multiplication in the C-star algebra. And in addition, we need to feed the matrix also with the same input. but there is no canonical way how to do this. Basically, what we need is to somehow fix some inner product on our C-star algebra, and then with respect to this inner product, we can take the dual of this map. So taking here the dual with respect to the inner product, and then we can formulate this condition. So in order to do that, we step aside and first we give more structure to the finite quantum sets. So if we have some classical algebras of functions, we have the integral or summation functional, using which we can define some bilinear form or an inner product, and the same we would like to have in the quantum setting. So having some functional which we interpret as an integral and define the bilinear form and inner product like this. And yeah, what I forgot to say here is that in order all this to make sense, we would like to expect that if we, as this adjacency matrix, take the identity matrix, which is in all bases look like this, then this entry-wise product, so here instead of A, I take not A, but just identity. So we would expect that this entry-wise product of identity with self is again identity, because this is what classically holds. So we would like to have it also here. So this is this condition. So again, I will write it diagrammatically like this. And what we also want, but we might not, but for my talk, I will also require this functional to be tracial. So if I take the functional applied to a product, then I can switch those two stuff. And it actually holds that for every finite dimensional C-star algebra, there exists a unique functional that satisfies those two conditions. So actually, we don't have to make any choice here. We have a canonical form satisfying those two conditions, which we can take here.
Daniel, I'm sorry, Daniel, there is in the theorem an M and an eta. Are both the eta M or I missed?
Okay, so yeah. I should have. Okay, so this M, this is a C-star algebra multiplication.
Ah, okay.
And this eta dagger, that's the functional.
And there is no compatibility between them.
Yeah, and the point is that, okay, I didn't say what is M dagger, I should have said that. So then we can construct this inner product, and with respect to this inner product, we can take adjoints, right? And so this defines, using the inner product, M dagger, which is, by dagger, I denote the adjoint with respect to this inner product, which is a map from Cx to Cx tensor Cx. So some sort of a co-multiplication, but it is not related to any quantum groups or whatever. And also I can take, by eta, I will denote the unit of the algebra. And if I take the adjoint of the unit, I get back this function. So this is why I denote it by eta dagger.
Ah, okay. I think if you take as a kind of inner product between two things, the evaluation, then the transpose with that is the co-multiplication, something like that. So it's not so far away from a co-multiplication.
So maybe you've heard the notion of Frobenius algebra. And
yes, of course. Okay.
Okay. Good. So, and well, if you want, you can also consider non-tracial functional, and then you obtain something different, which might also be interesting. Okay, so going back, this condition is replaced by this condition. So this is what I've already drawn here, like this. This is mimicking the condition that this matrix A consists only from zeros and ones. And I have this additional condition, and you probably are asking why I have star here, not a dagger. So yes, this is another, there should not be dagger, that the star is okay, and I define a star as the following thing. So I am not sure how much familiar you are with those diagrammatical calculi. So here, this diagram, this is my bilinear form. So this is sort of this
you read from bottom to top.
Yeah, I draw it from bottom to top. Yeah, because in literature about quantum graphs, they use this notation. Yeah, I was used to before to draw it from top to bottom. There are also people drawing it from left to right or right to left. So I think there's not a single convention, unfortunately. So okay, this is the bilinear form, which is what? Which is the M dagger composed with eta, I guess, eta dagger. Yeah, and like this, you can. Sorry, M composed with eta dagger. Yes, and by this I denote the dual of this the dual bivector of this bilinear form, and this is this A star. So and why this condition is here, this might be a bit unclear, and I agree that you can also define quantum graphs before without this condition. It will become slightly more clear in a minute, but in general, the idea is basically that this somehow corresponds to the condition that those elements of AIJs are real. So this star is like conjugating those elements of this adjacency matrix. And classically, from this condition, it already follows that the entries are zeros and ones, and they are automatically real. But in non-commutative geometry, this does not hold, and is exactly the fact that there are projections which are not orthogonal projections. So if you want this condition, you have to assume it extra. Okay, so this is the approach number 2. And again, you can define what undirected quantum graph means. This is, I guess, kind of straightforward, that this matrix A should be self-adjoint. So this is something else than this thing, right? So first, this is sort of the entries are real or self-conjugated, and this is like, in addition, that is self-adjoint, meaning that it equals to its conjugated transpose. Good. And now the no loop condition, now it becomes more clear what it should be. So classically, the loops in adjacency matrix are exactly the positions where there is 1 in this adjacency matrix. So if I take the adjacency matrix and perform this entry-wise product, which I denote by this bullet, then if there are no loops, then I should obtain 0. So that's the idea somehow, and build it up on this idea. Okay. So those are again the examples of typical graphs. So full graph. Okay, maybe the most easy one is the empty graph, which is just 0. Full graph is this eta times eta dagger. This corresponds to the classical fact that eta, that's the algebra identity written as a vector, is all one vector. So eta dagger is this all one matrix, which is exactly what a full graph should be. Then you might have this empty graph with a loop at every vertex. So classically, this is just an identity matrix. So this is why we put this also to the quantum case. And finally, you can have the full graph with no loops, just taking the full graph and subtracting the identity matrix. So those are the most simple examples. Good. And so now maybe it's good to think about what's the relationship between those two approaches. And the point is that those two approaches are equivalent. So approach number 1, this was considering a projection inside Cx tensor Cx. And I can take this projection and compose it with, in one entry, compose it with my bilinear form, and I obtain a map from Cx to Cx, which I can interpret as the adjacency matrix, and this adjacency matrix will satisfy the appropriate conditions. And conversely, if I start with adjacency matrix, I can compose it here with the dual of the bilinear form and obtain a projection in this algebra. So and this is where this op comes from. So if we want this to work, then it must be like this. Good. So maybe to summarize everything, this part is what I just told you. You can either follow the approach 1 and fix the projection and then define the adjacency matrix like this, or you can follow the approach 2, fix the adjacency matrix and define this projection here. And the idea is that this bullet product, this was this entry-wise product of two matrices, which we model this way. This exactly corresponds to the C-star algebra product in this setting, and the C-star operation exactly corresponds to this star operation that was defined this way here. So this is where it all comes from. So now it should become slightly more clear, I guess. And now I have all those conditions, undirected, no loops, loops everywhere, and so on. Some of those I already talked about. Maybe this subgraph condition is kind of interesting. If I have two graphs on the same set of vertices, how do I characterize that one is a subgraph of another? Well, this is by saying that the corresponding projection of the smaller graph is smaller than the projection of the larger graph in the sense that they commute this way. And if I want to rewrite this in terms of adjacency matrices, then this, again, this entry-wise so-called sure product appears here. Okay, so maybe, I don't know if there is some question to this summary. Okay, so maybe I can continue. So maybe it's time to have some more complicated examples. So, so the simplest finite dimensional C-star algebra that is non-commutative is the algebra of 2 by 2 matrices. And as I said, a quantum graph is just a projection inside the tensor product of those matrix algebras. And now I will already not write here this op. I will just use the isomorphism here, which will make it slightly simpler. And so this is actually isomorphic to 4 by 4 matrices, right? And if I want some projection in 4 by 4 matrices, then this is just characterized by a vector subspace of C4, right? So this is, therefore, it is really easy to come up with an example. So this is maybe what I wanted to highlight. So usually if you read some literature about quantum graphs, they would give you this second approach definition. And at least for me, it is totally unclear how to construct any example whatsoever. But if you think about it in terms of this approach 1, then it's really easy, I would say, because, well, taking a projection is just taking a vector subspace. And so we can do that. Oh, sorry. Okay. What I did here. Good. So for instance, you can take such a projection as an example. So this is a projection M4, projecting, of course, on the linear span of the columns of this matrix. And that's a quantum graph. Yeah. And maybe we can try to compute the adjacency matrix, how this looks like. So maybe first of all, I will rewrite it in a bit more suggestive form. If I draw such small matrices here, I can see this as M2 of C, or I mean M2 of C, right? Also, so I wrote it like this, and it's probably not obvious, but I guess you can believe me that this adjacency matrix, if you do this sort of rotation, what you obtain is a linear map from M2 of C to M2 of C, which is given sort of by this matrix in the sense that the canonical matrix 1, 0, 0, 0 maps to exactly this thing. So 1, 1, 0, 0. This is mapped to 0, minus 1, 1, 0, and so on. So it works like this. And you can also, of course, write this adjacency matrix really as a matrix if you fix some basis of M2 of C. So I take those matrices as bases, and then okay, so the image of the first matrix is 1, 0, 0, 1. The second one has 0, minus 1, 1, 0. The third one has 0, 1, minus 1, 0, and the last one looks like this. And now you can immediately see that this graph is undirected, so this holds. And you could also compute that it has no loops. So maybe we don't have much time already. So I will skip this, but it really is easy to compute with that. So that was what I wanted to show here. So yeah, do you have some question to this example? Okay, if not, then the second, what I want to talk now is how to do classification. And I guess this is already might be slightly evident from this example. So if you want to classify all quantum graphs over M2, you somehow just classify all projections, and all projections, those are exactly in one-to-one correspondence with vector subspaces. So that's the whole idea. And now you the only slightly complicated thing turns out if you want to classify up to isomorphism, which of course makes sense, which will make it slightly more involved, I guess. And so before I do to the go to the classification, here comes a third approach to quantum graphs, and this is basically what I just said. So more generally, every C-star algebra is of this form. So this is a direct product of matrix algebras, right? So a quantum graph is given by a projection in, oh, here should be a tensor product here, sorry. In this algebra, right? So equivalently, you can somehow rewrite this as a direct sum of NIC tensor M and JC, right? So the projection is given by a set of projections here. Well, and the projection here is just given by a vector subspace in this vector space. And just a technical thing you can do is, instead of considering this tensor product, you consider the space of linear maps between C and I to C and J. And this last thing is also possible to do, but this already maybe makes it maybe more complicated to understand than this characterization before. So maybe to give you some idea how quantum graphs look like. So this is a picture I tried to draw in my paper. I don't know how much sensible it is, but I think it's good to have some kind of picture in mind, although it's not slightly imprecise. So classical graphs, as I said, this is just vertices, and between those vertices you have some edges like this. And from this you can see that what a quantum graph looks like is that you have some sort of quantum vertices. So those are the summands here. And okay, and here classically at each vertex you can have at most one loop, but here kind of associated to every quantum vertex there's a whole vector subspace in, I don't know if this is M and C, then there's a vector subspace in M and C, sorry, of C n tensor Cn, characterizing some edges inside this sort of quantum vertex. And the same thing we have here, I don't know, MC, and here the edges inside are described by some vector subspace of Cm, tensor Cm. And now instead of just one edge here, you have some kind of quantum edge described again by some, okay, maybe this can be N1, 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 like this, N2, N2, N2. This is maybe V2, 2, and this is maybe some V1, 2 inside Cn1 tensor Cn2. So this is again some vector space characterizing all those edges here, and you have this for every pair of those quantum vertices somehow. And if you have just a C-star algebra consisting of a matrix algebra, then your set of vertices is just a vector subspace of Cn tensor Cn, and there's of course no point of drawing any picture because it just looks completely different than a classical graph. Okay, so now the idea is again to use this to classify those quantum graphs. And as I said, any quantum graph is given by such vector subspaces, and therefore if I take MNC for my C-star algebra, then quantum graphs are in one-to-one correspondence to vector subspaces inside Cn tensor Cn, which is actually you can describe this by again MNC, or maybe so that you don't have two MNCs in the same meaning, I decided to write GLN, which is the Lie algebra and general linear Lie algebra, which is the same as MNC, but that has a bit different notation for that. And also using Lie algebras is kind of convenient because the condition for no loops is that those linear maps here have trace 0, so those are actually inside SLN. If they are undirected, then this operator space is self-adjoint, so you could write something like V is inside the unitary Lie algebra. Taking those two together, you have V inside special unit Lie algebra.
Sorry, so here the dagger is the usual.
Yeah, here the dagger is the conjugate transpose of those matrices here. Yeah.
Do you have a meaning for the bracket if you're using Lie structure on one side?
Yeah, that's a good idea. No, I don't. Yeah, I'm not sure if this. Yeah, this may be interesting to ask, but I'm not sure if there's any meaning at all, or yeah, whether this is just a pure coincidence that those typical Lie algebras appear here, or whether it has any meaning. I'm not sure about this.
Yeah.
But you can use the theory of Lie algebras for the classification, because if you want to classify those quantum graphs up to isomorphism, then isomorphism of quantum graphs is given by some action of SUN, and you know how SUN, for instance, act on the Lie algebra SUN. So this I used to prove that simple graphs are determined only by the number of edges. Yeah, exactly. So yeah, I guess since I don't have too much time, I probably won't go into much detail here, but yes, this is what you can do. Yeah, basically the simple graphs are given by some vector subspaces of Lie algebra SUN, and in case of n equals to 2, you have SU2 is kind of like R3, right? you have this basis of Pauli matrices, and big SU2 acts like rotations, and you know that rotations, you can rotate any one-dimensional, like all vector subspaces of given dimension are equivalent up to rotation. So therefore, all quantum graphs with a given number of, or simple quantum graphs with a given number of edges are isomorphic. Good. So now just quickly to go to the second topic, which were those twists of Cayley graphs of abelian groups. There's the notion, oh, sorry, there should be quantum isomorphisms here. There's a notion of quantum isomorphism, which is basically some monoidal equivalence of some categories associated to those quantum graphs. But to stress the most important property for this application is that quantum isomorphism preserves what is called in the classical graph theory coherent algebra. So if you take this adjacency matrix A, you can first of all multiply the adjacency matrix with itself, for instance. So you have this multiplication, classical multiplication of matrices, and then you have also this Schur product, so this entry-wise multiplication, and you have the identity, and you have this all-one matrix, which is identity with respect to this entry-wise product, and those operations define you some algebraic structure which must be preserved by those quantum isomorphisms. So, right. And therefore, also the properties like being undirected, having no loops, and so on, those are preserved under this very natural notion. And therefore, this is like a sanity check that we defined those properties in a sensible way, right? And interesting question is how to construct some graph which is not quantum isomorphic to a classical one, because there are possibilities how to construct quantum isomorphic quantum graphs. So we wanted to have some quantum non-isomorphic graph. And the point is that it's enough to construct some graph where, given this coherent algebra, this Schur product is non-commutative, because classically it's entry-wise product of matrices, and therefore it must be commutative. So if it is non-commutative, then it is truly quantum or truly quantum non-isomorphic. And I constructed some examples here. First example is when the quantum graph, when the adjacency matrix or the projection cannot be compared to this identity in terms of the Schur product. So it neither somehow contains loops, nor it does not contain them. It's some sort of quantum, I don't know, superposition physicists would say, or something like that. So this is a pure quantum phenomenon that you can not have with classical graphs. So this forms an example of a quantum graph which is not quantum isomorphic to a classical one. Another example here is constructed with this matrix lambda 8. I call it lambda 8 because it's the classical name for it. It's one of those so-called Gell-Mann matrices forming basis of Lie algebra SU3. And if you really take the adjacency matrix corresponding to this SU3 element and compute A squared, so compositing it itself, and then using the Schur product, then this is not the same as this thing. So the coherent algebra is non-commutative with respect to the Schur product. And therefore, again, this is even, you can show this is a simple graph. So there is not this cheating with those loops. So this is a simple graph, which is not quantum isomorphic to a classical one. And lastly, this twisting of Cayley graphs of abelian groups. This is basically a well-known construction where you have, so if you take a Cayley graph of abelian group, so this is the algebra associated to the vector set of vertices, and of course this and the idea of Cayley graphs is that the group gamma somehow acts on this graph, or maybe I can say that this algebra co-acts on the graph, somehow compatible with this graph structure. And it's very well known that, okay, I instead of this C of gamma, I could also put here C of automorphism group of this graph or anything. And it's very well known that you can construct those co-module algebra twists given by some unitary bicharacters or two cocycles or whatever. And if you do this in this particular case, you obtain a quantum graph which is quantum isomorphic to the original one. So in particular, for instance, if you take the cube graph or the hypercube graph, it's already well known that if you do this twist, so a cube graph is a graph corresponding to the group Z2 to the power of n, or for a cube you have 3 here. And it is well known that if you do this cocycle twist, then you obtained so-called Clifford algebra. So the Clifford algebra should somehow describe some sort of anti-commutative deformation of those hypercube graphs. Okay, so that's it. Thank you for your attention. And
thank you, Daniel. Any questions?
Well, I have one. Have you worked on automorphism, quantum automorphism of those graphs or those quantum graphs?
again, so you are asking whether I studied automorphisms or quantum automorphisms?
Both, yeah. Quantum.
Yeah, both. Okay. Right. Yes. I, for instance, so for those twists of those Cayley graphs, that's quite simple because this commodule algebra twist works in such a way that okay, so we know classically how what is happening here. Oh, not this. Anyway, so classically we know we know the automorphism group, and we also know the quantum automorphism group, which act on this graph gamma. And this commutative algebra twist works in such a way that if I do the twist, so I have here some gamma tilde or whatever, then we also know how to twist this group or the quantum group. So we know how to what is the okay, maybe here should be G, right? For the graph. So we know how the quantum automorphism group looks like, because it's just the two co-cycle twist of the Hopf algebra or the quantum group. And as for those examples I had here, so here I had this classification, and it turns out that here I have just 4 graphs here, right? And this one is the empty graph, this is the full graph. So there are two interesting quantum graphs which popped up from this classification, and both are actually examples of the twisted Cayley graphs. So this also this way I also was able to determine the quantum automorphism group. What is maybe also interesting, yeah, I wanted to mention it here, but then forgot about that. The Junichiro Matsuda, as I said, he was studying also this question, the same question, this classification of quantum graphs over 2x2 matrices, and he worked in slightly more general setting, not assuming this this delta form to be tracial. So he considered also non-tracial delta forms, and this way he was able to prove similar theorem, but in a non-tracial setting, and he also studied the quantum automorphism groups. So he explicitly computed them, and there you see the Q deformations of the classical, I think, orthogonal group or something like that. Yeah.
And do you have a feeling that given a finite dimensional Hopf algebra over the complex, if you can realize as a quantum automorphism of a quantum graph or not? But how, if there are some invariant that from the quantum automorphism of suppose you have really a quantum a Hopf algebra that is built as a quantum automorphism of a quantum graph. Do you have an invariant that recovers the information of the quantum graph, so that given an arbitrary Hopf algebra, you can maybe guess it is a quantum automorphism of such an object or not?
Yeah. So I think you basically would like to have this Frucht theorem in the quantum setting, right? So classically, if you take a finite group, then you can realize this finite group as an automorphism group of some graph. And yeah, this is a very natural question. And of course, a lot of people had this idea. I also tried to think about this question. So now, So I agree that it is very interesting, and I think it might be possible to do this, at least if you somehow, if you would somehow relax the conditions of what your graph is. So if you know the classical proof of the Frucht theorem, then the proof goes like this, that you construct the Cayley graph of the group and you somehow color the edges, and in such a way that the automorphism group of the graph must be the group. So I'm quite convinced that you could do the same thing also in the quantum setting, but now the very complicated part is from this colored graph to obtain a simpler graph. Classically, you replace the colored edges by some clever constructions, and whether you can do this also in the quantum setting, I'm not sure. I guess it would be kind of complicated, but maybe somebody will turn up with some clever idea. Yeah, I will also try to think about this, but I think it's not easy.
Yeah, I was thinking about this in categorical meaning, because you can always reconstruct a Hopf algebra using categories by Tanakian construction. That's if it is a category of representation, something you take a factor of whatever. So the question is, do you have a categorical meaning for a quantum graph? I mean, there are representations of quantum graphs. Are these some particular tensor categories or something like that?
Yeah, this is, I mean, basically, what you can do is that you consider, this is what I wanted to say here, but didn't want to spend too much time on that. You can try to construct a category whose, for simplicity, let's say that the objects are just natural numbers and the morphism spaces are linear maps from Cn power k to Cn to the power L, where n is the number of vertices, basically. So this is the dimension of the C-star algebra, and you consider C to be the smallest such category that contains the multiplication morphism, the unit, and the adjacency matrix. And right, so this is, I would say, the canonical category associated to graph. And if you construct the associated compact quantum group, then this is exactly what is called the quantum automorphism group of the graph. Right, so it's like this. And yeah, but yeah, so
going back to the picture that you made before from a kind of boxes or circles for the quantum edges and big lines instead of edges and lines. It seems that a quantum graph is a kind of classical graph, but labeled by algebras and maps. So in that picture, do you think that maybe it could be convenient to consider weak Hopf algebras with basis the underlying classical graph instead of usual Hopf algebras?
And use now I'm not sure what is the weak algebra, but to use them for what exactly you mean?
I mean, or if you prefer a Hopf algebroid over those points. So can you go to the picture of the quantum graph as a picture?
A weak Hopf algebra is like a Hopf algebra, but where the co-multiplication is not co-associative. There is a
No, no, I don't mean that. I mean that it's co-associative, but it's not the co-unit is.
It's a quasi.
Well, I
okay.
think the name is weak, but I'm pretty sure the name is weak. But in any case, you can see this is a Hopf algebra in the category of bimodules over the k of q dots, if you want, it over the vertices. So in this picture, it seems like a quantum graph is a graph, a usual graph, together with a labeling or of matrices of some size of the vertices and the edges. Is it just a way of thinking, or it's well, maybe the question is that a way of looking at, or it's really a formal way?
Yeah, I'm not sure what was the good way to look on a quantum graph. I think that the most interesting examples probably are those where the C-star algebra is just a matrix algebra, and
so you have only one point. So the classical, the underlying classical graph is just a point.
Yeah, exactly. And then you have no classical structure and it's purely quantum. And if this is not the case, if the C-star algebra is some direct sum, then you have some mix of classical and quantum, maybe something like this. I don't know. Yeah, but the point is that somehow, for instance, using this quantum isomorphism, you pretty much can go from purely classical graph to a quantum graph. So the number of those, I called it quantum vertices, this is not a sensible invariant. What a sensible invariant is the dimension of the algebra. So this is really the number of vertices, like in the more in a different sense. So in this sense, I'm not sure if this is a good picture. I don't know. So this is just a, yeah, I guess way how to look at it. But
okay, but with that number, you can label with a natural number each vertex. So even if you have only one vertex, you can label with a number.
yeah, sure. Yeah.
There is that dimension.
Yeah.
Well, thank you. That's nice talk.
Any other question? Well, I will stop the recording.